So now we've made a very specific distributional assumption for you. When we said that U is normally distributed with mean zero and variance sigma square. Okay, so we have this very familiar bell-shaped curve which has U on the x-axis, and you have the probability density function that is plotted for you. So even though this assumption, these assumptions so far, including the sixth assumption, are required for statistical inference, even though we have these for convenience, we will see later that for very large samples where n is very large, we don't really need this sixth assumption. Okay, but for now we're going to keep it and perform statistical inference. So these six assumptions together are called classical linear model assumptions, or CLM assumptions. Okay, so the best way to think about these assumptions is to say that the classical linear model assumptions are the sum of the Gauss-Markov assumptions and the normality assumption. So these were the first 5 assumptions, and this was the 6th assumption. Okay, so now we can talk about the sampling distribution. So under the classical linear model assumptions, we can say that our estimate, notice our estimate beta hat j is normally distributed with mean beta j and variance beta hat j. Okay, and if you use the central limit theorem, then we can standardize this variable here and say that given a random sample of beta hat j's, so given a random sample of beta hat j's with mean beta j and standard deviation beta hat j, we can construct a variable like this, which has an asymptotic standard normal distribution with 0 mean and variance 1, or standard deviation 1. Okay, so this is coming from your central limit theorem, so you might want to review that. And the way we standardize a random variable is we take the deviation of that variable from its mean and divide it by the standard deviation of that variable. Okay, and that is going to be normally distributed or asymptotically normally distributed with mean 0 and variance 1. Okay, so the standard normal distribution with mean 0 and variance 1 will hold even though we're not conditioning on the independent variables here. Okay, but now the issue is that the standard deviation of beta hat j depends on sigma. Okay, and sigma is unknown, so we have to replace sigma with an estimator, which is going to come from sigma hat. Okay, and so when we replace sigma with sigma hat, we will move on to talking about the t distribution. Okay, so here this theorem, the t distribution for standardized estimators, states that under all the 6 assumptions that we stated before, this standardized variable has a t distribution with n minus k minus 1 degrees of freedom. Okay, so we're not proving this, but we're going to use this a lot when we do hypothesis testing. Okay, so your t statistics your t statistic here is basically defined as the deviation of your estimator from the hypothesized value in the population divided by the standard error of that variable.